Alright, so we're now going to move on to discuss the flight test equipment and the development thereof, which enabled these early studies of the aircraft's spin, starting with accelerometers. So the first accelerometer, or the documented development of the first accelerometer, was by Lindemann, who developed this kind of seismograph type apparatus to record normal acceleration in 1918. You can see a sketch of it here in this upper right hand figure. Essentially it consisted of a mass or a weight which compressed this spring on the left hand side under a load, and then that moved a pen which was in contact with a moving reel of paper, and that obviously gave a time history of normal acceleration, which could be correlated with the airspeed indicator readings, and therefore to line up some data for normal acceleration and airspeed. There was a problem with this though, and that was due to the high angle of attack, or the high angle of incidence during a spin. The airspeed indicator didn't really give very reliable readings because of its orientation. Obviously it wasn't exposed to the free stream when the aircraft was descending at such a high angle of attack. So Lindemann revised this, added additional dynamic pressure heads that were installed at an angle of 30 degrees, which was kind of the typical angle of incidence during a spin. And this allowed the data from the airspeed indicator to be slightly more reliable during the spin. This design by Lindemann was later refined by Zahm in the US, and basically Zahm's design comprised of numerous pens or styluses that were affixed above this moving reel of paper, and they all of the styluses had different tension springs associated with them, right? So at a certain G loading or normal acceleration, the corresponding spring would compress, which brought that particular stylus in contact with the moving reel of paper. So a very clever design, because you end up with some traces like you can see in that right hand side of the bottom figure there, and then you can just go and join up the endpoints of those lines to get a pretty accurate trace of normal acceleration. The disadvantage of this though is that the resolution of the trace is only as accurate as the number of styluses and the spring constants basically of that setup there. So depending on how the instrument was set up, the number of styluses, obviously it starts to get very impractical the larger this apparatus becomes. The next development in accelerometers was by Norton, who at the time worked for NACA. He was an expert in optics, so obviously looked at redesigning the impractical accelerometer solutions that we've just discussed into something a little bit more neat. By the way, Norton had also previously developed an accurate airspeed indicator, and therefore looked to move into redesigning the accelerometer. So you can see a sketch of his design here. It incorporated a spring, which you can see here at one end, and then the deflection of this spring under load caused the mirror to rotate. This mirror reflected a beam of light, projected it onto a moving film, which you can see there on the right hand side, and therefore basically again plotted a trace of essentially normal acceleration versus time. There was one very crucial, ingenious addition to this design, and that was that Norton used an electromagnet to dampen out the spring's vibrational resonances, which was key because it reduced the noise in the data. The accelerometer, Norton's design, was found to be accurate to within 0.01 of a G, but only when the acceleration was in the normal plane. And it was noted that reliability of the readings were pretty significantly reduced when accelerations in other planes other than the normal plane were introduced. So finally then, with regards to the development of accelerometers, the RAF in the early 20s were developing what became a standard instrument pack for flight tests, and that contained two separate accelerometers, one for normal G and one for lateral G. And this particular design comprised of a very sensitive semicircular section of quartz fiber, which was illuminated by a lamp, as you can see in the top sketch here, and under loading the quartz fiber would deflect, and then the movement of it was recorded onto a moving film for analysis. This particular instrument was recorded to be as accurate as up to 0.1 of a G. But again, this was limited to when the accelerations occurred in only the normal and lateral directions only. So this was similar to the Norton design that we just discussed. Again, another optical solution. Similarly to this, another development over in the States, Reed at NACA, who was busy refining Norton's design from a few years earlier, developed this accelerometer, which was capable of measuring accelerations in the three mutually perpendicular directions simultaneously. So for the first time, able to give us accelerations in three axes. The design had shutters on the individual lenses. They would open and close at different timing intervals, so that you got, for the three traces on the time history, you got solid dotted or dashed lines based on how quickly the lens opened and closed. So that was ingenious. It allowed you to differentiate between the different accelerations in the different planes. So the kind of the overriding kind of results from this particular period were reasonably successful, matched the mathematical modelling that was going on at the time pretty well as well, and generally it was accepted that for your accelerometer to perform as best possible, it needs to be located as close as possible to the aircraft centre of gravity, and therefore also not shifting the aircraft centre of gravity around by putting some instrumentation that could potentially be heavy somewhere else on the aircraft. So next we're going to discuss control position recorders. So what is the pilot doing with the stick in the cockpit, and how can that be correlated to all of the other data that we're trying to collect? Well, the first control position recorder was developed by the RAF, which was also part of this standard instrument pack that they were developing in the early 20s, as we've just discussed with the accelerometers. Basically, it comprised of a number of pens or styluses which were physically linked to the control surfaces with a series of pulleys and levers, and obviously that was very impractical and was kind of susceptible to go wrong. The technique kind of was again refined very much so by Norton, again using optical techniques, as he had done with the accelerometers. As you can see, a photo of his control position sensor here on the slide. Basically, the motion of the controls were transmitted to the instrument that you can see a sketch of here via some cords which wrap around 3 separate drums, right, for the 3 different control surfaces. And then the motion of the drums were transmitted via levers which rotated or kind of deflected mirrors which were reflecting beams of light through a film onto a lens. So again, Norton used different shutter speeds so that the different dotted lines could be distinguished, and again it was quite a nice, neat, ingenious optical solution to basically a mechanical problem. So control position recorders were vital for demonstrating different types of spins, as we've discussed earlier. So next we're going to discuss rate of turn indicators for analyzing angular velocity. Well, the RAF, again, for this standard instrument pack, also contained 3 gyroscopic rate of turn indicators, which you can see in the sketch here on the slide. Basically, the 3 gyroscopes, they were driven electrically, 18,000 RPM, and they were fitted to kind of like a base plate at right angles, and they were kind of like suspended in free air with springs. And as the orientation of the axis of rotation of the aircraft changed, then the corresponding springs would deflect. And this deflection was transferred via like an arm to a stylus, again, which reflected a beam of light through a lens and then onto a film. So again, another optical solution, this time for a rate of turn indicator. And from this, the angular velocity of the aircraft could be calculated based on a simple proportional relationship of the spring deflections. And the rate of turn of the aircraft could be synchronized with other standard equipment from the aircraft, and therefore we're building up quite a nice profile of what the aircraft is doing during a spin. So this RAF rate of turn indicator allowed the angular velocity about the 3 principal axes to be recorded pretty accurately, and this was documented for the first time by Hardy in 1921. There was also a NACA version of this rate of turn indicator. They developed an angular velocity recorder in 1922, and the US were also developing a standard instrument pack for flight tests, which contained the NACA airspeed indicator, accelerometers, control position recorders that we've just discussed, and this rate of turn indicator. And Reed approximated that this particular instrument was accurate to as much as 0.01 radians per second. This document also states that the accuracy of some of the other instruments, plus or minus 2 miles an hour for the airspeed indicator, plus or minus 0.05 G for the accelerometer, and plus or minus 1% for the control position. So all in all, a pretty handy little pack of instrumentation to have there to go and conduct some flight tests, and that's exactly what they did with particular regards to the spin. Okay, so let's finally discuss a few other flight test techniques and types of instrumentation that were also in development at that particular time, starting with attitude indicators and this idea of trying to visualize the flow around the airfoils in a stall. Well, the first documented use of something like this was by Lindemann, who fitted a rod which extended out from the wing strut of his biplane and attached a length of tape to the end of it. And he hoped that in flight the tape would align itself with the oncoming free stream, and give some indication of the angle of attack or angle of incidence to the pilot during spin. However, he concluded that the tape fluttered around too much to make any more than a basic estimation of angle of incidence, and this was in 1918. Jump forward a few years, Flight Lieutenant Haslam fitted multiple strips of fabric to the trailing edges of the lower wings of his biplane for his studies in 1928 to 1932, and he observed that under pre-stall conditions the cloth streamed rearwards as expected, but when the aircraft was stalled, the cloth actually lay forwards flat against the wing and fluttered around sporadically. So obviously what he had observed there was the aircraft or the airfoils stalling and the flow separation, and therefore the strips of cloth not aligning themselves with the free stream flow anymore. So these two tests basically prompted this idea that we still use to this day of using many small wall tufts completely covering the airfoil section to give a more comprehensive understanding of what the airflow is doing, where this flow separation occurs first, how the stall develops. And this is a technique still used to this day, as you can see in this top right hand photograph up here, which was a photograph taken for some research that I conducted recently with one of my colleagues from Cranfield, which was looking at the stall development on a Slingsby Firefly light aircraft. So now moving on to discuss a little bit about the development of altimeters. Well, the radio altimeter was developed in 1926 and basically worked by transmitting a beam of radio waves to the ground and then analysing the time it takes for the aircraft to receive that reflection back. By the way, a similar system was also fitted to an aircraft forward looking for collision avoidance reasons, and the method that the radio altimeter used differed to that of when the barometric altimeter was invented a few years later by Colesman, because it basically gave the pilots their height above the ground in the current location directly, right? So then we would like to understand what's going on with the angle of attack and angle of side slip during the spin as well. So vanes started to be introduced. The first documented use of vanes for spin testing was by Hardy in 1928. Obviously the positioning of vanes are highly dependent on how good the data is from them. Even at this stage, the readings from the vanes were only regarded as an indication of angle of attack or side slip, because even at this stage it was recognized that the influence on them by the aircraft itself as the air flows over and around the aircraft, influencing the angle of attack and the local angle of attack and side slip. So the way around this, obviously, that we use today is to extend a boom out of the nose of the aircraft or out of the wing of the aircraft, for example, to get the vane in as close to free stream conditions as possible. And booms were first introduced by Canada in the 70s and later by Kirshner. Also, with the development of film cameras, certain research institutions were looking at cinematographic methods, like the development of small cameras that could be fitted to aircraft, for example, and this really started to take off in the 1970s when this kind of technology was getting more and more miniaturized, and researchers could fit cameras to the fuselage or in the cockpit over the shoulder of the pilot, for example, to give a better picture of what's going on during the spin. So In recent years, despite kind of observed lull in flight testing of the spin, obviously further refinement of and development and miniaturization of technology means that flight test capability these days is more accurate and more wider ranging than ever before. As an example to this is a miniature 7-hole probe data system used in spin testing by Lee. This piece of equipment is just 4 millimeters in diameter and weighs only 150 grams, and it's capable of measuring flow angles to an accuracy of 1%. So just as an example of how technology is pushing this field of research forwards. Something that I've used in the past for flight test research programs, an SPG systems AHRS, attitude, heading and reference system. As I say, I've used that before. Weighs I think just under 40 grams, but can provide 3D attitude and acceleration data during dynamic maneuvers such as the spin. So that's just an example of how technology is pushing this field of research forwards, and how more and more accurate and faster frequency data, for example, is capable now than ever before.